Let's take a look at this problem taken from the British Mathematics Olympiad Round 1. Here we have the value of 34 factorial with 4 digits hidden. Find the values of these digits without using a calculator. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. We need multiple tools or tricks to determine each of the missing digits. The first one that I'm going to approach is the digit B. That should be over here. Notice that the number of trailing zeros as in how many 0 at the end of the number of this factorial can be calculated by 34 over 5, the integral part of this fraction, and then 34 divided by the next power of 5, again integral part, and we can add this sum forever. But for this number 34, the terms afterwards are just 0 because 25 is the largest part of 5 that is less than 34. So we can focus on these two terms. Now we have 34 over 5 is 6.8, so integral part is 6 plus 1, and that's 7. So from this we know that there should be 7 zeros at the end of 34 factorial. And from the digits we have, we only see 6, so that means B has to be 0. The rationale of using this sum is that it's just to find the power of 5 when we do the prime factorization of 34 factorial. We can say this 2 to some power times 3 to some power, but for the power of 5, we know that that should be power to the power 7. So from this, we can at most produce 7 zeros because each 0 is actually produced by multiplying 2 by 5. But we must have powers of 2. The number over here, the index, must be larger than 7. The next thing I would like to calculate would be the digit A. That's over here. That can be achieved by looking at the number 34 factorial divided by 10 to the power 7. As in, what happens if we ignore all the zeros? So 34 factorial divided by 10 to the power 7. I'm going to really list out the prime factorization of the factorial. So for power of 2, there should be 17 even numbers. And then there are 8 multiples of 4, 4 multiples of 8, and then 2 multiples of 16, and 1 multiple of 32. And so altogether we have 17 plus 8 plus 4 plus 2 plus 1. Factors of 2 added all together. That's 2 to the power 32 multiplied by 3 to the power 11 multiples of 3, 3 multiples of 9, 1 multiple of 27. And for power of 5, we know it's 7. We've done that already. That's because we have 6 multiples of 5 and 1 multiple of 25. While for 7, afterwards, that should be much easier because we don't have any prime squared anymore. So 7 to the power 4, 11 to the power of 3, 13 to the power of 2, 17 squared, and then the other primes would be just not even squared, it's just single prime. So 19, 23, 29, and 31. All of these primes multiplied together divided by 10 to the power 7. So from this we have this cancel out, and for this we can subtract by 7, and so we have removed the entire denominator. But do not worry, we do not have to multiply them, we just have to find the units digit of this product. So tidying up the powers, we have 2 to the power 17 plus 8, 25, 29, 31, 32, minus 7, which is 25, times 3 to the power 15, 7 to the power 4, 11 cubed, 13 squared, 17 squared, 19, 23, 29, and 31. Now, to find the units digit, we can find them one by one. For 2 to the power 25, we know for powers, they actually repeat itself every 4 powers. Okay, so if we multiply by the digit itself, every 4 times, the last digit repeats. So because 25 is 1 mod 4, so we know it must have last digit to be 2. Mod for 15 is 3 mod 4, so it's 3 cubed, and that's 7, because 3 cubed is 27. 7 to the power 4 is 2401, so the last digit is 1, and then 1, 9, 9, 9. All the rest can be done by direct multiplication. So for this is mod 10, and we can do them one by one. 2 times 7, 4, and then we have lots of ones. We can ignore them. 9 times 9, 1. For each pair of 9s, we can create a 1, and the last one can be ignored. So that means from this we know the quotient 34 factorial divided by 10 to the power 7 has the last digit equal to 2. So from this we know A equals 2. To use the divisibility test of 9 and 11, we have to add the digits and to add alternate digits respectively. So I've replaced A and B by 2 and 0. I've crossed out the 7 ending zeros of this number because they do not affect our outcome, and so we can consider fewer digits. So I've labeled alternate digits with yellow and green, so we're going to add them up separately. For the yellow group, green group over here, so 2 plus 3 plus 6 plus 0 plus 8 plus 6 plus 4 plus 0 plus 1 plus 0 all the way. While for the green group, we have 5, 4, 9, 6, 1, 7, 8, 4, 4, 6, D. We have unknown digits over here. 9, 7, 3, 5, and 2. And the sum of these two groups are 61 plus C for the yellow group and 80 plus D for the green group. Now, if we add them up, that means 141 plus C plus D has to be a multiple of 9. And simplifying, we can say C and D has to be congruent to 3 mod 9. While for the difference, we have to do 61 plus C minus 80 plus D, and we need that to be a multiple of 11. And C minus D, we have the number minus 19 at the left, and so we know that that should be minus 3 mod 11. So now we can try out the cases. So C plus D can either be 3 or 12. Well, for the mod 11 equation, be restricted by the nature of C and D, they have to be digits. They have to be integers between 0 and 9. So that means that difference can only be either minus 3 or 8. And in fact, C minus D equals 8 is very unlikely. The only outcomes can be 9, 1 or 8, 0, nothing else. And both cases will not give us 3 mod 9 if we add them up. So we can quickly reject this case That means C minus D has to be minus 3. Now we can go back to mod 9, and we know that if we add up these two numbers, like the one in this row and the one in this row, they have to be even, because it's about equations about sum and difference of two numbers. So by comparing parity, we know that we must take C plus D equals 3 and C minus D equals minus 3. And so that means we have C equals 0 and D equals 3. So together with A equals 2, B equals 0, this is our final answer, 2003. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.